Hello everyone. I'm Baoyu from Guangdong University of Technology. Today, the talk title is Products of Linear Alkylbenzenes over MWW zeolite nanosheet. So first, look at the map. Our university located in the south of China. It's near Hong Kong and Macau. I will talk about my research from 3 points. So the first is background. The linear alkylbenzenes (LLB) is the raw material for the production of alkylbenzenes sulfonate. The alkylbenzenes sulfonate is a surfactant. It's widely used in household and industry detergent. So right now, the main catalytic technology for the production of LAB is hydrofluoride. The issue for the hydrofluoride, it has serious corrosion, environmental pollution, and toxic, and has lower selectivity to the target to LAB. So it's necessary to develop a solid acid catalyst for a green product of LAB. In the past decades, the clean hydrochloric acid and liquid zeolite has been intensively investigated. But for clean hydrochloric acid and liquid, they have some limitations in the production of LAB because lower selectivity, small surface area, and inferior stability. Zeolites have exhibited good performance in the production of LAB because they have high stability, tunable acid side, and high selectivity to LAB. But for a alkylation between benzene with dodecyne, the size of products is larger than the reactant. That means for the traditional microbes of zeolites, a small microbe channel can be easily blocked, resulting in the activity of catalyst. And another problem is for the microbes zeolites, active site, the most powerful active site located in the interior of zeolites, it can limit the access between active site with reactants. So it's leading to lower activity for the zeolite in alkylation. So fabrication of hierarchical zeolites is an effective way to solve this problem. The key for fabrication of hierarchical zeolites is shorting diffusion pathway, such as the fabrication of nano-sized zeolite to synthesize two-dimensional zeolites with nanosheet structures, and the introduction of additional defects or misprops in the framework of zeolites. In present research, we focus on two-dimensional MWW zeolites. So for a two-dimensional MWW zeolites, it greatly decreases the thickness of zeolite framework. On the one hand, it can enhance the diffusion for reactants and products. And on the other hand, because it greatly decreases the thickness of zeolite framework, it can expose more active sites. That means most of active sites located in the 12 memory range symbol cups located on the external surface of MWW zeolite. And means it can improve the accessibility of active site. So here is the three structures for two-dimensional MWW zeolite, including multiple layer MWW zeolite and single layer MWW zeolite and pillared MWW zeolite. All of this structural information of two-dimensional MWW zeolites has been investigated, and their catalytic performance in the alkylation has been evaluated in this research. So the content of research including 3 points. The first one is tuning the texture property of a catalyst. In previous research, the thickness of two-dimensional MWW zeolite was tailored. It's expected to tune the mist power and micropore porosity. Second is tuning the active site location in a catalyst, especially for a Brunstone acid, especially for the distribution of Brunstone acid site on the external surface and internal surface. And the third is optimizing the catalyst performance in order to improve activity and selectivity simultaneously. So here, the dual template strategy has been employed to fabricate single layer and multiple layer MWW zeolite nanosheet, which expect to improve active site activity in the catalyst reaction. So for a conventional three-dimensional MWW zeolite, the HMI has been used as a structure direct agent, but for a two-dimensional MWW zeolite, the HMI and line-chain quaternary ammonium surfactant has employed to fabricate a two-dimensional MWW zeolite. Here, the ligands of surfactant has been tuned to 16, 14, and 12. By tuning the amount of surfactant in the synthesis gel, the multiple layer MWW zeolite and single layer MWW zeolite has been produced. We also fabricated a pillared MWW nanosheet. Here, the effect of the silica-aluminum ratio and the structure of pillared MWW zeolite and their catalytic performance has been investigated because based on the silica-rich framework and aluminum-rich framework of MWW zeolite, it keeps different structures of pillared MWW zeolites. So here is the X-partner for the conventional MWW zeolite. We call it MCM22, but for MZN means MWW zeolite nanosheet. MZN4 and MZN8 means different percentage of surfactant in the synthesis gel. For 12, 14, 16 means the ligands of surfactant. So from this XRT partner, we will find the MZN4 exhibit similar X partner with the conventional MCM22. It means tuning the ligands of surfactant chain is not enough to generate a single layer MWW zeolite, and only the multiple layer MWW nanosheet could be produced. But for MZN814, it exhibits different 101 and 102 peaks compare MCM22 and MZN4 samples. So it means MZN814, the single layer MWW zeolite could be produced. So page gives the SEM and TM pictures for MZN4 samples. From this picture, we will find the MZN4 exhibit nanosheet morphology. We also give the SEM picture for the conventional MCM22 and typical MZN814. So from the SEM photo, we will find MCM22 showed a broad nest-like shape. This is the typical morphology of our commercial MCM22. But for typical MZN814, it presents a interpenetrating network of nanosheet with ultra-thin fluid-like morphology. That means increasing the amount of surfactant is an effective way to eliminate MWW zeolite. We also give the TEM and AFM photos for a typical MZN814 samples. So from this picture, we will find the MZN814 present ultra-thin nanosheet morphology, and the thickness of MWW zeolite is about 2.5 nanometers, and which means the single layer MWW nanosheet produced. For MCM22, it only showed a typical three-dimensional characteristic with a thickness of about 23 nanometers. So this table also gives the texture property for a resultant zeolite. So from this data, we will find the MWW zeolite nanosheet exhibit a higher fraction of external surface area and miscible volume compared MCM22. This table also gives the acidity for a MWW zeolite. So from this data, we will confirm that the MWW zeolite nanosheet exhibit higher external porosity acid side compared to the conventional MCM22. This picture just shows the catalytic data for a MWW zeolite and conventional MCM22. So from this picture A, we will find compare conventional MCM22, the resultant MWW zeolite exhibit higher conversion. And because the MWW zeolite has a higher concentration of external porosity acid side. But for all of this, MWW zeolite exhibit comparable selectivity toward 2-LOB, and we will explain and discuss this problem in the following slides. Look at this picture C. This is a very interesting result. Poison experiment for pyridine and DTBP poison experiment. So for a pyridine poison experiment, the catalyst absolutely lost their activity because the pyridine can poison all of active sites in the zeolite. For DTBP, because it's a large molecular site, it can only poison porosity active site located on the external surface of MWW zeolite. So for a DTBP poison catalyst, the activity decreased by 82%. It means the porosity acid site located on the external surface is the main active site in the present alkylation reaction. We also built in a relationship between conversion with the external porosity acid site. So from this picture, we will find the conversion of MWW zeolite is important to concentration of the external porosity acid site. So this picture just gives the distribution of alkylated products. So from this picture, we will find the selectivity of 2-LOB is rather stable. Here we also give the computer simulation results. So this is a computer simulation. We calculate the binding energy between the LOB isomers with the 12 memory cage located on the MWW zeolite surface were calculated. So from this picture, we will find the 2-LOB and the highest binding energy and best matched the steric configuration with the 12 memory cage located on the MWW lamellar surface. That's why the MWW zeolite exhibit the highest selectivity towards 2-LOB. And this is the exopartners and the process distribution for a period MWW. zeolites. So from this XRT pattern, we will find the period MWW zeolites exhibit long-range ordered structures. And from this pulsar distribution, we will find the period MWW zeolite exhibit obvious mystical structures compared to conventional MCM22. Here we also give SEM and TEM photos for repeated MWW zeolite. So from this SEM picture, we will find repeated MWW zeolite exhibit plate-like morphology, and for repeated MWW zeolite, it also exhibits lamellar structure. And the thickness of zeolite framework is about 2.5 nanometers. This table also gives a text parameter and aesthetic. So from this table, we will compare MCM22 repeated MWW zeolite exhibit higher fraction of external surface area and miscible volume, and repeated MWW zeolite also exhibit higher concentration of external Bronsted acid site compared MCM22. Answer why repeated MWW zeolite exhibit higher activity compared to conventional MCM22. And here, repeated MWW zeolite 74 means the silicon result displayed the highest activity among all of these investigated MWW zeolite because they had the highest concentration of external Bronsted acid. So all of these MWW zeolite exhibit comparable selectivity towards true LIB because it is special topology of MWW zeolite discussed in above. So we also gave a stability test for repeated MWW zeolite. So from this circle experiment, we will find the repeated MWW zeolite emphasize strong stability compared to conventional MCM22 due to enhanced diffusion property. So this table also gives the effect diffusion time constant. So from this table, we will find the effect diffusion time constant of repeated MWW zeolite almost 4 times the rate of MCM22. This is the actual pattern for the price and spending and MWW zeolite. So from this picture, we will find repeated MWW zeolite exhibit robust stability in the alkylation reaction. So this is the TJ curves for the spending MWW zeolite. So from this picture, we will find repeated MWW zeolite exhibit lower content of hard coke compared conventional MCM22, and why repeated MWW zeolite exhibit good stability compared conventional MCM22. So this is a conclusion. Multiple layer and monolayer MWW zeolite nanosheet were fabricated through a dual-time strategy, and all the repeated MWW zeolite expressed the more accessible Bronsted acid site for alkylation. Result is all the repeated MWW zeolite exhibit super selectivity toward true LIB and exhibit extraordinary resistance toward deactivation. So this is the picture for research group, and thanks to the funding supports and the collaborators' help and the students' hard work. This is my email. So if you have any questions, please feel free to contact me. Thank you. Thank you. Bye.